yesterday. And so I will be talking about enumerative geometry of curves. I will be counting curves, and in the simplest possible setting, the most classical setting of counting curves on surfaces. And the general theme of this talk will be the interaction between the various ways to count curves, or various meaning you can attach to this question. In particular, we'll be talking about counting complex curves and counting real curve. It is what is Welchanger invariants are about. They are part of real algebraic geometry. They have to do with counting real algebraic curves. And to go between them, we'll talk about tropical curves. And something which at some point will be the key of the story will be that even if you care about a surface S, it will be essential to think about it as being part of a three-dimensional geometry. And if you have a surface S, the simplest way to cook up a three-dimensional geometry is simply to multiply by a trivial third factor. That's a copy of C. Or if you want something compact, you can multiply by a copy of P1. And you can think of that as simply the total space of a trivial line bundle on your surface. But on any surface, there is another natural line bundle, which is the canonical line bundle. So instead, you might look at the total space of the canonical line bundle as a natural threefold attached to your surface. And so these various objects will appear at some point in the talk. So let me start at the beginning with the most classical story, which is over complex numbers. And actually, I will restrict myself to the simplest kind of surfaces, which are rational surfaces. And very specifically, so for every n, I will denote by Sn the surface obtained from P2, complex projective plane, by blowing up n points in general position. So blow up of P2 at n general points. So I have a blow up map to P2, and I will denote by E1 to En the exceptional curves. So they are all -1 curves, which are created by the blow-up. And now we like to count curves in this surface Sn. And to start with, we'll only count rational curves. In Sn, so a rational curve, you can think, so in the simplest possible case, it will just be a map from P1 to Sn. So count of rational curve in Sn, and you want to fix the homology class of some class beta in the homology of this surface, and I can write this class as the form dh minus sum over ai ei, where h is a pullback of the class of a line in P2. Okay, so this thing comes from a degree d curve in P2, and it intersects each of the ei with multiplicity ai. And if you look at the rational curves of this homology class, if you look at the expected dimension of the moduli space of this curve, the expected dimension is first chain class of the surface intersecting with beta -1, which is, if you calculate, is 3D minus sum of the ai -1. And I will denote by m this number, and I will always consider class beta such that this number is non-negative, so I assume that. So I assume that the expected dimension is non-negative, that there is some moduli space of such a curve. And then to get a number, I will simply impose my curves to pass through the correct number of points in your surface, and the correct number of points is this m. So passing through m general points. So you expect to get finitely many such curves and to get a number. And we'll consider the number obtained from this counting problem, which is given by a Gromov-Witten series. So I will get this count. I will get the corresponding Gromov-Witten invariance. I will denote GW0 because it is integer 0, class beta of my surface Asn. And it's possible to show that in this setup, this genus 0 Gromov-Witten invariant is always some non-negative integer. If you're in the Del Pezzo situation, if n is at most 8, it's possible to show that if everything is indeed in general position, there are actually finitely many such curves. And they are all very nice. The image of these curves, they have at most nodal singularity, so they're all very nice curves. And this thing is the honest count of this curve. If n is strictly bigger than 8, you are no longer at Del Pezzo. And to define this number, you need some virtual class in algebraic geometry. Or if you have symplectic geometry, you need to perturb the almost complex structure to reduce to the case where there is really finitely many such curves. And then this thing is a count of this kind of perturbed pseudo-holomorphic curves. And here I will go through two running examples for this talk. So here is example 1 and example 2. So example 1 will be the most classical case where n is equal to 0, so that the surface is just P2. And I will look at the class which is simply degree 3 curves in P2, so cubic curves in P2. And so we're looking for rational cubic curves in P2 passing through M, which in this case is equal to 8 points. And if you looked at Conan's t-shirt yesterday, you should know that the number of rational cubic curve in P2 through 8 points in general positions is equal to 12. Yes?
Is it obvious from the algebraic geometry perspective that these are integers?
So it's not obvious. So
but you can be proven using algebraic geometry.
It can be proven by algebraic geometry, and it has been proven by Götze Pandey in '98.
By computer.
So actually, it has been proved by algebrogeometric reasoning that the moduli space is actually 0-dimensional, but possibly non-reduced with some multiplicities.
Thank you very much.
One can argue that there is really no stacky automorphism, even algebrogeometrically in this setup. Yeah.
Maybe just a related question. If you plot more than 8 points, then can you say that the number of curves that you're counting is the actual number of curves in some deformed?
That's from a symplectic point of view. If you take if you perturb the complex structure to a generic almost complex structure, then it becomes some honest count of curves.
Okay. Thank you.
Yeah, the moduli space becomes a reduced collection of points.
Also in higher, if you blow up many times.
Yeah, that's right. Yeah, for any n. Yeah.
Thank you.
Okay, so this thing is this very classical number, 12, rational cubic through 8 points. So it's a nice example. The example that we really care about is maybe slightly more involved. If n equals 6, so S6 is like P2 blown up in 6 points. It's like a cubic surface. And I will take the class beta to be 6h minus some from I from 1 to 6 to EI. So they come from degree 6 curves in P2. And they intersect each of the 6 exceptional curves with intersection number 2. And in this case, if you calculate this m, you get 6 times 3, which is 18 minus the sum of this number minus 12, which is 6, minus 1, so you find 5. So you're looking at rational curves in this cubic surface, in this homology class passing through 5 points in general positions. And these numbers have been calculated by Götze Pandey, again at the end of the 90s, and it's 3,240. It's an interesting number because it's a number that physicists got wrong. There is some physics paper containing a wrong prediction for this number, and I think Götze Pandey were very happy to correct this number. Okay. And the last thing I want to say about this number, which is actually how you get this number, is that in some sense these numbers are not mysterious. You can calculate all of them using the WDVV equation, associativity in quantum cohomology. Okay, so in the case of P2, it's this famous Kontsevich recursion formula counting rational degree D curve passing through 3D minus 1 points. And what Götze Pondai did at the end of the 90s is that this WDVV, associativity quantum cohomology, is like strong enough to determine all of these numbers for any n, not just P2, but P2 blow up in n points for whatever value of n. And using this recursion relation, you can, for example, calculate this number. So this thing will be the complex side of the story. And now let me say something about the real side. So I will still denote by Sn the blob of P2. And now I will view P2 as a real algebraic variety. And for the purpose of this talk, you can think of a real algebraic variety as a complex algebraic variety equipped with the action of the complex conjugation, so equipped with the anti-holomorphic involution. And here I consider the standard real structure on P2 with fixed locus of this anti-holomorphic, with real locus is just a standard real projective plane RP2. And then instead of blowing up n general points in CP2, you can blow up points in CP2 which are all real. So blow up of P2 at n real points in P2. So you take points like in RP2 and you blow them up. Then the result will have a natural real structure whose real locus, you can check that each time you do this real blow up, what you do at the real locus is take connected sum with an extra copy of RP2. So actually this thing is RP2, connected sum RP2, like n plus 1 times. Okay, so what you get are like the non-orientable compact topological surfaces as like real locus of this real algebraic surface. And now you might try to do the same thing. You might fix the same homology class beta and the same number of points.
Blow up is a complex blow up. It's not like a real blow up.
Yeah, that's right. So okay, if I view the thing as a complex thing with something, as a complex thing, I do the ordinary blow up.
Okay.
But I think the induced operation on the real point is like the real, on the real locus is like the real locus. It's like the real blow up. Yeah, yeah. So you like to count.
Sorry, do you allow blowing up a pair of real points?
Oh, yeah, that's, so if you want to produce a surface having a real structure, something you can do is blow up points which are real. But it's also fine to blow up pairs of complex conjugated points. Like, see now that the configuration of points is like globally invariant, but like not individually fixed. And for the purpose of this talk, I will assume that all the points are real. And it's a very interesting question what to do if you blow up a pair of complex conjugated points, and it will be, it's not covered in our paper, but it's a very interesting future direction. And if you do that, the real locus might have a more interesting and different topology. Sometimes the real locus might have different connected components, and so on and so forth. So yeah, so there is a rich collection of real structures you might consider, and I'm considering the simplest possible one, where I blow up purely real, only real points. And then you might want to count now real rational curves. So they are really like mapped from P1 with this standard real structure with real locus is RP1, mapping to this surface in a way like compatible with a real structure. And the basic issue, if you try to answer this question, is that the answer is not an invariant in the sense that it might depend on which configuration of points you pass through, and it might also depend on which configuration of points you blow up to construct your surface. The thing is not an invariant. And it's a basic issue if you try to do real enumerative geometry. So if you think about the complex case, in the complex case you get an invariant. And one simple way to think about it is in the complex case, these general conditions, when they failed, when things are not general, it happens in codimension 1, but it happens in complex codimension 1, which is real codimension 2. And so you can always go around if you move through, if you follow some kind of general path. But if you try to do real algebraic geometry, then everything is real. These moduli spaces of, and here it's again real points for the problem to make sense. This kind of collection of real points here or real points here. If you look at the set of like, if you look at the moduli space of such a points and to the kind of bad loci, they are real codimension 1. So the complement might be a union of different connected components. And when you go from one to the other, there is no reason for this count to remain the same. And actually, even in the simplest possible example of rational cubic curves in P2 passing through 8 points, if you ask what happens over the real numbers, depending on what is the configuration of 8 points, you might get 8 curve, 8 real curve, 10 real curve, or 12 real curves. So you might get different answers. So what Velchanger realized in the early 2000s is that there is a way to fix this problem if you count this curve with a correct sign. If you do a sign count of these curves, then you will get a number which is independent of everything, of the precise configuration of points and the precise blown up points. So Velchanger explains that if you have such real curve, like P1 to Sn, let me call it F, a real rational curve, you should count it with a sign. So you should attach each a sign plus minus 1. And what is this sign? So here is the recipe that Velchanger gives. So you look at these rational curves, and then up to perturbing the almost complex structure for any n, this curve is as nice as possible, meaning the image is like as at most nodal singularity. So you look at the image of this curve. So it's a curve with nodal singularities. And then you look at the nodes which are real. So the nodes might, so because the curve is real, the nodes are either real or come in pair of complex conjugated nodes. And if you look at the nodes which are real, there are two types of nodes. So in complex geometry, all nodes are the same. They are all x, y equal to 0. But in over the reals, x squared plus y squared equal to 0 is not the same thing as x squared minus y squared equal to 0. Because if you look at the real locus of that, you think it's just a union of two lines. Whereas the real locus of that is like a single isolated point. So there are two types of real nodes. There are cis1, which are something called elliptic or isolated, and cis1, which are like non-isolated in the real locus, which are called hyperbolic. And the Velchanger recipe is to take minus 1 to the power the number of elliptic nodes. Okay, so given a curve like that, you can go through the nodes. You see are they elliptic, are they hyperbolic? And you do minus 1 to the power the number of elliptic nodes. And then, so you sum these numbers, you get the Velchanger invariance W beta Sn, which is some integer, which goes the Velchanger invariance. And in this case of cubics in P2, you can check that this number is equal to 8. So whatever the configuration of points, you always get 8. So sometime here when there is 10 curves, typically what will happen is that some of them will contribute with minus signs, and the total sign count will still be 8 anyway, and similarly here. So definitely because it's a count with signs, this Velchanger invariance is always some lower bound for the true number of real curves.
When you say that the picture is always at worst nodal, that means like that's like a generic picture, or like? Yeah. So this thing, and actually it's a technical issue which will come back later, which is the only way I know to define Velchanger invariance for general n is through symplectic geometry. So you perturb the almost complex structure,
And then it's a fact that there are finitely many such a curve like that, and in the image they all have at most finitely many nodes, and no worse singularities.
Okay, that's, yeah, symplectically, but then there's no, what's the involution? Like, what does real mean in that?
Okay, so here I'm only looking at real curves. So like symplectically, you look at pseudo-holomorphic curves, so from a Riemann surface with an anti-holomorphic involution, mapping to Sn with its anti-holomorphic involution. And when you perturb the almost complex structure, you need to take an almost complex structure which is compatible with this involution. The involution should remain anti-holomorphic. So yeah, you need to set up things. But it's like the most natural thing you might do. And what you need to prove is that, yeah, it looks as nice as possible. Yes?
So if I have this like elliptic thing,
Yes.
and I move, like suppose my moduli space is not zero-dimensional, it's
Uh-huh.
positive-dimensional, then if I have a point and I move found nearby one, the elliptic singularity would turn into a circle, right? And on the other side it would go away. I guess what's strange is that it's confusing even from the symplectic perspective or from any perspective, the elliptic things are not at all, are like non-generic. Because that's like two spheres touching your real point.
So like from the point of view of this, like because we're in dimension 2, I think it's kind of generic. Like if you have a curve which has a node, and if it stay like, I mean, I'm looking at threshold curves, I think my curve will generically have a node. So if we were in dimension 3, it will be very non-generic to have nodes. Like typically the nodes will open. But in dimension 2, it's a kind of generic behavior because.
I think there's just a topological formula.
Yeah, that's right. So for example, I mean, like the total number of nodes is topological, and yeah, and so here, the finer information is a division into elliptic and hyperbolic, which might vary from curve to curve.
Oh, so you could reinterpret that number in terms of the number of hyperbolic.
Yeah, that's right. So because the total thing is topological, you might do that. Yeah, and I think it's only some like historical reason people prefer to say elliptic. You could say hyperbolic, and it will only differ by global signs.
So why is the number of nodes is topological? Can it be all even conjugate pair?
Yeah. That's right. So the number of so I need to. Let me try. So definitely the total number of nodes is the non-real one come in complex conjugate pairs. So the parity of real nodes is topological, and this thing is only about the parity anyway because it's only sign. So the number of real nodes is not topological, but the kind of parity of the total number of real nodes is topological because the non-real one come in pairs. Yeah, it's about.
Can you draw a picture of what like a bifurcation that gives rise to a pair of elliptic and hyperbolic nodes looks like? Like, is there a simple example?
Yeah, so I will. Okay, so to prove this theorem, like the main theorem is that there is, if you do that, there is some invariance. And the exercise I will not do, but the kind of basic bifurcation is what happens when you create the cusp. So think to a real cusp singularity and think of perturbing that and see what happens. And the claim is that if there is a one parameter real deformations, and on one side, anyway, the exercise is to do that, and it is Welchanger's proof, essentially. So this is local model. And actually, it would be much better to have some more conceptual proof of invariance, but I don't think it's really the case. Okay, and I think, by mistake, I erased my example. So here I have the example with 12 and 8. And this example with 3,240. And if you calculate the Welchanger invariance for that, you find 1,000. And in the same way that there is some WDVV equation calculating all these genus 0 complex Gromov-Wheeler invariants, there is some recursion relations, first proposed by Solomon and proved later by other people. There is some kind of real or open analog of the WDVV equation which provide recursions for these numbers and which are strong enough to calculate these numbers. And so here maybe the comment, if you are more of a symplectic geometer, is that one way to think of this kind of real curves, instead of thinking of a curve with an involution, if the curve is really like, for example, as in our case, it's really P1 with fixed locus is P1, and this thing mapped to Sn, and the real locus goes to the real locus inside Sn, and the real locus inside Sn is like naturally a Lagrangian submanifold of Sn. And so instead of thinking about this sphere with this involution, you can cut the sphere into two and just think about a disk whose boundary is on this Lagrangian submanifold. And so you should think about this Welch-Singer invariants as some examples of open Gromov-Wheeler invariants, which you might want to think of count of, in the simplest case, of counts of, let's say, holomorphic disk with a boundary on a given Lagrangian submanifold. And in complete generality, there is no reason to expect such numbers to be well-defined or to define invariants. And you know from symplectic geometry, the natural way to organize curve with boundaries not into numbers, into some infinity algebra, because module spaces of curve with boundaries themselves have boundaries and so on. But in few situations, you might be able to extract numbers out of this data. And the Welch-Singer invariance is one example where you can do that. Okay, so if you're a symplectic geometry, you might think of this count as counting particular count of just disk with boundary on this Lagrangian. And then this sign, this mysterious sign from this point of view, has been reinterpreted by Solomon in terms of natural orientations living on module space of like holomorphic disks in Floer theory. Okay. So this thing has a complex and real side of the story. And the general theme of this talk is some kind of interaction between the complex and real pictures. So there is something remarkable, which has been discovered by Bloch and Gutcher, which is, in some cases, there exists a natural polynomial into one variable q, which interpolate between the count of complex curves and the Welch-Singer counts of real curves. And the setting in which they could define this number is, from the point of view of this talk, a quite restrictive setting, is that if Sn is toric, which is the case if n is at most 3. If you blob P2 and n points in general position, if n is at most 3, you can view that as naturally as a toric surface. Like you can take your points to be the torus fixed points in P2. But if n is strictly bigger than 3, it's no longer possible, and so Sn will no longer be toric. So under this kind of very strong assumption, if n is like 0, 1, 2, 3, but not more, Bloch-Gutcher were able to define some polynomial, I will denote by g beta Sn of q, which are polynomial with actually non-negative integer coefficient. Actually, it's a Laurent polynomial, so in some variable q, with a remarkable property that if you set up, if you set q equal to 1, you get the Gromov-Wheeler count. And if you set q equal minus 1, you get the Welch-Singer count of real curve. And the point of this toric assumption is that the definition of Bloch-Gutcher is not really geometric. They do not say what this polynomial is really counting. They use the fact that this geometry is toric to be able to calculate the complex and real curves in terms of tropical geometry. So essentially, because the curve is toric, there is some c star squared inside it. And if you take log of moduli of modulus of coordinates in c star squared, you get some kind of map to R2. And the kind of curves you care about here, if you look to the image here, there are some kind of amoeba. And if you take some correct limit, if you send the points, your points constrained to infinity in a proper sense, in the limits, these amoebas will give you some tropical curve, some kind of trivalent graph in the plane in R2. And it's the theorem of Michaelkin that in this toric setup, this count of complex curves can be calculated by counting these tropical curves with some weight. And it's also a theorem of Michaelkin that if you care about the count of real curve, you look at the same set of tropical curves. The only difference is the weight you assign to each tropical curve. So from tropical geometry, so somehow tropical geometry gives a kind of ways to interpolate between the two pictures, because the same set of tropical curves is relevant for both problems. The only thing which is different is the multiplicity you assign to a given tropical curve. And what Bloch-Goetsche observed is that there is a natural way to refine this multiplicity you assign to a tropical curve. And the basic refinement is that, okay, so in general, a tropical curve relevant in this problem looks like that. It's like trivalent. And the contribution of this tropical curve is a product over the vertices of some multiplicity, which is determined by the local picture around this vertex. So this thing is a multiplicity to get a complex count. And what Bloch and Goetsche suggest is simply to replace this integer mv by the q integer mv, which is simply 1 plus q squared plus q to the mv minus 1. And maybe I want it to be invariant and q goes to q inverse. So I symmetrize q minus mv minus 1 over 2. And so the observation is that, okay, so by construction, when q equals 1, you get the complex multiplicity, so you get the complex count. And the non-trivial observation is that if you set q equals minus 1 in this formula, you get exactly the multiplicity which is relevant to count real curves with very charged signs. And so what they suggested is to define this polynomial by looking at this tropical curve, and you weight then with this q integer, and you get this polynomial. So for example, for this 12 and 8, so this thing was just P2, which is toric, so you can do that, and you will get q plus 10 plus q inverse, which indeed for q equal 1 give you 12, and for q equal minus 1 give you 8. But this definition is kind of non-geometric. It's true tropical geometry. It only makes sense in a toric situation. So for example, for this example here, which was about the cubic surface for n equals 6, is non-toric. So here there is no definition of a Bloch-Goetsche polynomials. And so the general point of our paper, or at least the starting point, is can we define some polynomial, like some generalization of Bloch-Goetsche polynomial, which will work for any n without toric assumption. And so to do that, so because we want something we work beyond the toric situation, we can no longer use the simplest form of tropical geometry. Instead, it will be much better to have some geometric definition of some polynomial, which in the toric case we cover Bloch-Goetsche polynomials. And then, but because it's geometric and does not use a toric assumption, it will be valid for any n. And then you might ask that it still has these remarkable properties. So the claim is that to do that, there is something which is not obvious at all, and it was not obvious at all from maybe any viewpoints, is the following definition of what I will call BPS polynomials. And the way we think about it is starting from the complex story. So we start with, so this thing will really be defined using some Gromov-Witten viewpoint. You want something which is related in some limit with genus 0 Gromov-Witten invariance. And then somehow you want to refine this number. You want to find an extra variable q, so that when q equals 1, you recover your genus 0 Gromov-Witten invariance. So the problem, so one way to phrase the question is you have your Gromov-Witten problem, counting rational curves through a number of points. Can you find an extra variable, like an extra deformation of the problem? Okay, so extra deformation of like of this number. And so if you just think about what are the possible parameters in your problem, maybe the obvious thing you might want to vary is that here it's genus 0, so you might ask what about replacing 0 by any genus? What about looking at curves of any genus? And of course, there is a basic issue with doing that. So here, I increase the genus, but I keep the curve class, and I keep the number of mark points. So now the expected dimension for this problem is no longer 0. So now the expected dimension is like G. It's like if you think in P2 passing to 8 points, if you look at genus 1 curves, then you get the one-dimensional pencil of cubic curves. And so you no longer get something of expected dimension 0. Okay, so maybe it looks like it's a bad idea. Or instead, what you might say is that, okay, if you really want a number, you just need to integrate a correct cohomology class of degree G to get a number on this G-dimensional moduli space. So you should define this number as some integral over. So here, I look at the corresponding moduli space satisfying the constraints. And this thing is G-dimensional. And I want to put a G-dimensional class. And I will put minus 1 to the G, lambda G, where lambda G is a top lambda class. And it is a top chain class of the Hodge bundle. So this thing is something you can consider on any moduli space of genus G Riemann surface. If you have C a Riemann surface, you can look at the space of one forms on it. This thing is a G-dimensional vector space. And so if you have a moduli space of curves, there will be a corresponding rank G vector bundles made by these spaces. And then you can take the top chain class of this rank G vector bundle. It will be a class of like complex degree G that you can integrate over this virtual class of expected dimension G to just get a number. And here it's essential. So previously in genus 0, everything was, okay, if you do everything correctly, generically, there was really finitely many curves, you get the integers. Here, at least from the surface point of view, there is really a non-trivial moduli space of stable maps. And you do some non-trivial intersection theory on this moduli space, and so in general, you get some rational numbers. This number has not the obvious counting meaning. You might ask, where does this class come from? Like, why is it the natural choice? So the point is that this class has a very natural interpretation if you think about a counting problem not in a surface, but in a threefold. So you should think of these numbers, I claim that this thing can be interpreted as a Gromov-Witten invariant of the threefold Sn times P1. So here is my surface. I add an extra direction. And but I really want the same counting problem. So I will look at curve which live in a fiber of this fibration over P1. And I would even impose some constraints that the curve live into one of these fibers. So here are the curve I want to count. So actually from the moduli space of such a curve is exactly the same moduli space as before. So you might ask, what do you gain by doing that? The point is that in dimension 3, the expected dimension of a moduli space of genus G stable maps is independent of the genus. So if it is 0 in genus 0, it's 0 for any genus. So actually from a three-dimensional point of view, if you are able to like perturb the almost complex structure in a random way, then this family of curves should become like finitely many curves. And now maybe with some orbifold issues, which will produce this rational number. And if you ask what is the relation between, and here it's like honest Gromov-Witten invariance of the threefold without extra insertion. But if you want to express it as a Gromov-Witten invariance of the surface with some insertions, if you compare the obstruction deformation theory of a curve in the surface or in the threefold, the difference between these obstruction theories will exactly produce this class. So Okay, if you try to vary the genus from a surface point of view, the expected dimension becomes too big. But if you think to the problem from a threefold point of view, the expected dimension should be 0 anyway, whatever is the genus. And so you should have well-defined number. So you get these numbers, which are rational numbers. And now we'll use some further magic of dimension 3. So the first magic, which is like, in some sense, completely elementary, is that the expected dimension is 0 for any genus. The second piece of magic is the expected BPS structures of Gromov-Witten invariants of threefolds. So if you are counting curve in dimension 3, because the expected dimension is independent of the genus, you get a number for every genus, a rational number in general, and you can form generating series of these numbers. So here I call this number, and maybe with my correct normalization, the correct thing to write is that, so a sum over G. So you get a power series in some formal variable I call U. And the BPS structures is telling you that actually this infinite sequence of rational numbers is determined by finitely many integers, which are called BPS invariants. And you can rewrite this series in terms of these finitely many BPS numbers, as I will denote BPS G beta Sn. And then here I need to write the correct formula. There's this function 2 sine u over 2, which appears. And so here this thing on the threefold is only the correct formula in the Fano, so-called Fano class situation, if you look at a curve class which has positive intersection with C1, but which will be the case in our setup because we assume a curve class has positive intersection with C1 of the surface. So it will be the case here. So here we use the fact that C1 of Sn dot beta is positive. And in this case, at some heuristic level, if you try to understand, okay, what is that in some kind of geometric way? So one reason you get rational numbers in Gromov-Witten theory in higher genus in dimension 3 is that if you have a curve of genus G, which is a solution to your problem, you can always take a curve of genus G prime, glue it to your genus G curve, and map it to a point. It's like you can have contracted components, which means in your moduli space there is this kind of full moduli space of genus G prime curves, which are like doing nothing, apart from making your expected dimension wrong, because these things are like big, higher dimensional spaces which appear in your moduli space. And you should think of this 2 sine over u over 2 sine function as some kind of universal contribution of this contracted component. So this strange function, 2 sine u over 2, if you expand it in power series in u, it's just like simple rational numbers which capture something universal about the intersection theory of genus G Riemann surfaces, genus G curves. And the heuristic is that if you remove these contracted contributions, what remains should be some kind of honest count of beta BF curves, which would be integers. And this structure has been proved by symplectic method. In the Fano case situation, the fact you get integers has been first proved by Zinger. And here the non-trivial statement is like there are finitely many G such that this thing is non-zero. So there are finitely many of them, finitely. And the fact that finitely many of them has been proved by Do and Valpuski in the Fano class situation. So using symplectic methods, essentially you can argue that if everything is generic enough, the curve really roughly look like that. There is really nice, I mean, in the first approximation, it's not fully correct, but I would say there is really this finitely many nice curve contributing these numbers. And then everything else is obtained by adding these contracted components, which contribute these kind of universal contributions.
Maybe this is a very specialized point, but how do you go from the symplectic counts to the algebrogeometric counts? Like somehow part of your story is algebrogeometric, I guess, and part of it is symplectic.
Yeah, that's so. Yeah, so here, yeah, so it's true that if you want to do everything properly, so yeah, it depends what you are happy to refer to or not. I mean, I could just say, as a symplectic and algebraic, genus 0 Gromov-Witten invariants are the same. Or, for example, you could say, I always use the symplectic definition. And what we will actually prove will be the Del Pedo situation, and you need to know the standard complex structure is like the generic one somehow, and this thing is just true by some standard argument. It's one way you can organize.
So all these definitions are actually symplectic Gromov-Witten invariants throughout the story.
Yeah, that's yeah, you can say it like that. Yeah. Or I think, or you might believe the claim in the literature that they're the same as algebraic. So.
It is a claim in the literature.
Yeah, definitely there is some claim in the literature that they're the same. They're the same, yeah. So you get these finitely many integers, and now you can just organize these finitely many integers into a polynomial in a variable Q. So I will define, so here's some definition. So actually, an extra comment is that in the Del Pedo situation, we'll ultimately we'll do some kind of calculation which will give some different proof that this structure and these BPS numbers exist. But beyond the Del Pedo thing, I will definitely need some symplectic. I don't know non-symplectic definition. So BPS polynomial, I define BPS beta Sn of Q as being the polynomial. So it's not exactly, there will not be exactly the coefficient, but there will be, okay, I will write -1 to the G, Q minus 2 plus Q inverse to the G. So the thing is a Laurent polynomial with integer coefficient. So roughly the factor here is like the same thing as this sine factor to the power 2g. I just remove that to get a polynomial, where q is related to u by some exponential change of variable. Okay. So the claim is that all these classical looking counts of rational curves in rational surfaces, they can naturally be upgraded because, okay, in genus 0, we recover the old count. And by construction, so if you do q equal 1 in this polynomial, if q equal 1, you will see this thing will be 0. So you will only get the genus 0 contribution. And in genus 0, the BPS number just recovers the Gromov-Witten number. So actually, this is BPS polynomial coming from the Gromov-Witten theory of the threefold, S times P1, provides a natural way to kind of refine these very classical count, like enumerative count of rational curves in rational surfaces. And now the first theorem, and of course this thing makes sense actually for any surface. We don't use anything about Sn. It makes sense for any surface, as long as I look at the class beta with this type of assumption. So the first theorem is that if n is less or equal than 3, so if you are in the toric situation, in which case the Bloch-Gottsche polynomials were defined long ago using tropical geometry, then actually the Bloch-Gottsche polynomials coincide with the BPS polynomial. And this thing is a not obvious statement at all. It's saying that somehow these higher genus Gromov-Witten invariants somehow can be described using tropical geometry in the toric situation. And what happens at the end is exactly replacing the ordinary multiplicity by this Q integer multiplicity. And the whole point of the story is that now the right-hand side makes sense for any n. There is no longer any toric assumption to define this polynomial. And the remark is that so by construction, this polynomial at q equal 1 gives a complex count. And the mystery will be, why on earth at q equal -1 does it have anything to do with real algebraic geometry? Because this thing is some purely complex Gromov-Witten theory count. It's just counting homogeneous complex count. It is threefold. We never discuss the real structure anyway. But it is true for Bloch-Goetsche polynomials that for q equal -1, you get the Welschange count of real curves. And so the natural conjecture, or like natural hope, is that if these polynomials are really the kind of correct generalizations of the Bloch-Goetsche polynomial for any n, the conjecture is that for any n, if you look at this BPS polynomial, and if you write q equal -1, then this thing should be equal to the Welschange count of real curves. And a priori, there is zero geometric reasons to believe such statement because this thing captures homogeneous complex Gromov-Witten theory of the threefold S times P1. This thing captures real rational curves in this surface Sn with this standard real structure. So there is no geometric connections, obvious geometric connections between the two. But the conjecture is that if you know homogeneous Gromov-Witten theory, somehow you know zero real Gromov-Witten theory. And okay, so the first piece of evidence is in the Bloch-Goetsche case is known, and the proof is that in the Bloch-Goetsche case is toric. You can compute everything tropically, and some of the combinatorics describing one side happens to be the same, and so it's true. But the whole point of this conjecture is to ask what happens for any n. So before stating the final result, let me make a comment about these nice examples, 300, 240, and 1000. So it was about the case n equals 6. So now we have a definition of a kind of generalization of the Bloch-Goetsche polynomial. We have this BPS polynomial. And so you could ask, what is this polynomial? And the claim is that you can calculate it. I will maybe say one word about that. And so here is some interesting polynomial, which is like a new polynomial in some sense. Okay, so here is some interesting Laurent polynomial with integer coefficients. And by construction, it has to be the case that if you write q equal 1, you get 3240. And we're really happy when we plug in mathematical q equal -1, you get 1000. So in this example, the conjecture is true. This polynomial, this BPS polynomial really interpolate between these two numbers, which were known a long time ago. And now the main theorem, which is where actually all of the work of the paper is going, is that the theorem is that the conjecture is true for all n less or equal than 6. So like for 4, 5, 6, which are fully non-toric, then the conjecture is true for any curve class. And it's very, very likely that exactly the same technique we'll use will work for n equals 7 and 8. It will just be more painful. But one reason we don't go beyond the Del Pezzo situation is that, beyond the Del Pezzo situation, you will really need to work properly symplectically, because the only proper definition of the Welschange invariance really require working symplectically. So here you can work, so here the claim that in this setup, you can work with the standard complex structure because it's already generic enough for every purposes. But beyond that, you will need to do something symplectic. So the claim that this conjecture is true. And so how to do that? So this proof will not give any geometric insight, like deep insight for why the conjecture is true. It will just prove it. And it will prove it by somehow calculating both sides in some way. And we run some degeneration arguments on both sides and decompose one side into like simple elementary pieces and check that these pieces matches. And if the full structure match, the two will agree. So the proof, okay, so and maybe, yeah, so in 2 minutes. So let me say, so even if this result is for n less or equal than 6, we actually prove a version of this result for any n, which is a slightly different result. Instead of looking at Sn, which is P2 blow up in n points in general position, we can look at the surface Sn tilde, where the n points all lives on a conic. So this thing is a conic in P2. And you blow up the n points on this conic. It's like a non-generic version of Sn. And now in this geometry, what you can do is to count rational curves as before, but relatively to this conic. So you count your curve with some tendency conditions along this conic. And in this setup, we prove a version of the conjecture for any n. We prove that in this setup, there is some relative version of the BPS polynomials, which for any n captures some relative version of the BPS polynomials. And then for n less or equal than 6, we can use some degeneration argument from the situation where the 6 points are blown up generically to the situation where they are blown up like in a special positions to relate this story to this story. And in this story, we use some degeneration. And at the end of the day, there is some tropical-like combinatorics. There is some story of flow diagrams. Which were studied by Erwan Bruegele in the classical context of genus 0, complex, and real curves. And the real work involved tracing the higher genus Gromov-Witten theory through these degenerations arguments to check that they are compatible with both sides. Okay. There was a further story I will not have time to discuss, which is at the beginning. I promised that there will be something to say about the non-compact Calabi-Yau threefold KS, but I will not have time to talk about that. So let me leave it here and stop there. Thank you.
Any questions? Yes.
What about KS?
You asked my questions.
Yeah, so already for usual block-Gottschall polynomials, there is some conjecture of Gottschall and Chandler, which is that this polynomial should have a completely different meaning. So when you see a polynomial like that, maybe the obvious thing you might want is maybe this polynomial is a Poincaré polynomial of some space. Maybe these numbers are Bethe numbers of some space, maybe. And it's roughly what Gottschall-Chandler conjecture for the usual block-Gottschall invariance, and so we conjecture something analog for this general BPS invariance. And the conjecture is that these BPS polynomials are equal to, okay, so here are some words, genus 0 refined BPS invariance of KS. So whatever these words mean, they're supposed to be some kind of virtual version of a Poincaré polynomial of some Modic space of sheaves on the non-compact Calabi-Yau threefold KS. And again, maybe there should be no reason to believe this conjecture because this thing has to do with higher genus Gromov-Witten theory of S times P1, or maybe S times C inside S times P1. And you might say there is no reason to believe such a thing. But for example, if you look to what happens when S is a K3 surface, actually this thing is a known fact that in some sense is what is something called the Katz-Clem-Waffa conjectures, the higher genus regeneration of Yau-Zaslow is saying higher genus Gromov-Witten theory, the universal generating series of that is captured by essentially Poincare polynomial of Hilbert scheme of points on the K3. So I claim that for K3 this type of relation is true, but of course you could say for K3 it's maybe less surprising because Ks is actually equal to S times C. But for something like P2, Kp2 is very different from P2 times C. And the only reason to believe this conjecture as I know is a physics heuristic that as usual you should not, okay, there is really string theory living in dimension 10, so really there is a Calabi-Yau fivefold which is Ks times C2. And inside this Calabi-Yau fivefold there is both Ks.
So S is a K3.
So actually for this argument S is any surface. So here there is both Ks and there is S times C. If C is one of this C2 factor. And the claim is that if you go through what is expected from, I don't know, 10-dimensional string theory, you might arrive at this type of prediction. But currently this thing is completely open. Even in the toric situation, the Gutters and the prediction is still open. But it will still be like still another way to think about this polynomial, which is completely different looking.
So you're saying that we find where is the quantization operation?
Yeah, I mean, it's saying like there is two ways to quantize the genus 0. Either you can use this refined thing on Ks, which is like using Beatty numbers instead of Poincare polynomial, or you could use higher genus Gromov-Witten theory on S times C, which does not use any refined thing in the classical sense. It's like unrefined, usual Gromov-Witten invariance. But some of the same, it should be two ways to do the same thing.
What is Q minus 2 plus Q minus 1? Is that some, should I think of this as some Beatty numbers or something?
Yeah, so for this1, yeah, I don't know. For this formula, I don't know. I should point out in the classical 12, it's clear. Maybe this thing is a Poincare polynomial of the rational elliptic surface. Q plus 10 plus Q inverse. The rational elliptic surface has Beatty numbers like 1, 0, 10.
Is it that you get circle?
Sorry? Ah.
The minus 2?
Yeah, that's also. Yeah, I think the answer is yes. It's let's say it's some version of a Poincare polynomial of the elliptic curve. But actually, I'm not really, because there is something kind of wrong with the grading. So this is supposed to be, here I claim it's a rational elliptic curve. This thing is supposed, yeah, anyway. I think it's not fully clear what's going on here.
This is related to our work, like cover, I think the cover we also
Yeah, that's okay, so maybe it's a good point. So this conjecture is a version of a sequence of relations which appear in several places before. And so, for example, in some work with Longting, we explore some higher genus Gromov-Witten theory, like relative or log Gromov-Witten theory of some surfaces, and we show that in some cases that there's some interpretation as refined DT invariants of some quiver, which are objects of the same nature. So indeed, in the work with Longting, we prove a statement which fit in the same philosophy, which should be explained by that. And this thing should be another example of this philosophy. Yeah, exactly. And actually, what Julia will talk about next will be maybe like a classical version, like some genus 0 Gromov-Witten will be related to some kind of a classical DT type statement in a, again, quiver-related setup. But not, this thing is like a geometric setup.